Hi, this is Alex from devstories.eu. OpenCV, Computer Vision Deep Dive, Episode 17 of 20. For decades, computer vision engineers believed you needed two cameras to calculate true distance. You needed stereoscopic vision to triangulate points in space. Today, AI models can perceive physical distance from a single flat image by interpreting shadows, texture, and scale, just like a painter does. This breakthrough is called deep monocular metric depth. People often confuse relative depth with metric depth. Relative depth is simply knowing that a sofa is in front of a wall. It is a sorting of visual layers. Metric depth means knowing that the sofa is exactly 2.4 meters away from the camera lens. Until recently, pulling absolute metric measurements from a single picture was considered mathematically impossible. A single two-dimensional image loses all inherent scale. An object could be small and close to the lens, or massive and far away. Deep learning models bypass the classical geometry problem entirely. Instead of triangulating points across two lenses, networks like Depth Pro learn from massive datasets containing millions of images paired with ground truth 3D depth maps. When you feed a single standard image into the network, it does not look for stereo disparities. It evaluates monocular cues. It analyzes texture gradients, noting where surfaces look smoother the further away they are. It processes contextual lighting, occlusion, and the known physical scale of recognizable objects. The model then builds a dense, pixel-by-pixel prediction of absolute distance. Here is the key insight. Modern architectures accomplish this without knowing your camera intrinsics. You do not need to feed the network the focal length, the field of view, or the sensor size of the camera that took the picture. The network infers the focal length directly from the visual content of the image itself. This creates a zero-shot solution. You hand the model a photo taken by any random uncalibrated lens, and it outputs a precise, absolute depth map. Think about an augmented reality application on a standard smartphone. A user wants to see if a new dining table fits in their home. They stand in an empty room and point their single rear camera at the floor. Classical AR requires you to move the phone around to generate parallax and slowly build a spatial map. With deep monocular metric depth, the application processes a single static frame instantly. The neural network calculates the exact volume and dimensions of the floor space in milliseconds. The application then renders a virtual table into the camera feed, perfectly scaled to the real world, planted on the floor at the exact right depth. Under the hood, achieving this requires massive receptive fields in the neural network architecture. The model uses vision transformers to capture global context. It looks at the entire image at once to understand the overall geometry of the room. It then combines this broad view with high-resolution local processing. This dual approach allows the model to produce sharp depth boundaries around complex edges, like the thin legs of a chair or the leaves of a houseplant. It completely avoids the blurry, bleeding-edge artifacts that plagued earlier depth estimation models. The fundamental shift is the ability to extract absolute spatial measurements from a single, completely uncalibrated image frame. That's all for this one. Thanks for listening, and keep building.